Hello and welcome to episode 27 of ToKCast. I say 27. On YouTube it's episode 27, but if you go to iTunes or if you go to Podbean or one of those other places where the audio-only versions of these podcasts come out, you'll find the numbering is slightly different. There are more audio-only versions of ToKCast than what there are video versions. All of the beginning of Infinity material is definitely on YouTube, however. Okay, so we're still on chapter 11. This is the multiverse. It's part 4 now of the multiverse, and I'm anticipating today that we'll finish the multiverse. So I'm going to be sticking reasonably closely to the book today, but also at the end we're going to do a little bit of a short story. And the purpose of the short story is to emphasize exactly how the multiverse is indeed a testable theory, and testable against other ways of looking at quantum theory that have been tried over the years. The other so-called interpretations. So we tend not to call the multiverse an interpretation of quantum theory. We tend to just call it quantum theory, in the same way that dinosaurs are just how we explain what fossils are. We tend not to add on this whole idea of dinosaurs are our interpretation of fossils, even though they are, but they are the only interpretation of fossils. They're the only scientific interpretation of fossils. And in the same way, if we take quantum theory literally, we are kind of forced into this idea of the multiverse because it is simply a literal reading of what the equations are saying. In particular, I like to refer to the Schrodinger wave equation. So the Schrodinger wave equation describes all the, for example, positions in which an electron can occupy around a nucleus. And there's a variety of them simultaneously. And so taking that literally means that the electron really is in these different positions. Now, not in the one universe, that's not possible, but although there is a sense in which the electron is spread out around the nucleus, as we've talked about before, it has this kind of ink blot character, as David describes it in the beginning of Infinity. But more than that, it extends across many universes, occupying all physically possible places across the multiverse around that nucleus. But let's go back to the book. Now, recapping what's been said in previous episodes, we've been talking about this story where there are people on a spaceship that has a transporter and the transporter malfunctions. And in one spaceship, the transporter malfunction causes a spark, which causes a person to spill some coffee, which then causes them to have an interaction with another person, which leads to romance and so on. And in the other universe, there is no such spark, there is no transporter malfunction. So we have this differentiation of the universes that prior to which the spark or malfunction happened, we had fungible universes. We had two universes, but they were absolutely identical in all respects. And then this deterministic law, this deterministic event, causes the universes to differentiate. And we had a story going on so far about that. It's a fictional story. And diving straight back into the beginning of Infinity, David writes, "In the real multiverse, there is no need for the transporter or any other special apparatus to cause histories to differentiate and to rejoin. Under the laws of quantum physics, elementary particles are undergoing such processes of their own accord, all the time. Moreover, histories may split into more than two, often into many trillions, each characterized by a slightly different direction of motion or difference in other physical variables of the elementary particle concerned. Also, in general, the resulting histories have unequal measures. So let us now dispense with the transporter in the fictional multiverse too." Let's pause there in my reflection. So only in very contrived quantum experiments might we get equal measures, by which we mean 50-50. So let's say, for example, we have a photon heading towards a half-silvered mirror. Now, we can contrive the experiment there such that half of the instances of the electron go straight through and half of the electron's instances get reflected off. That's where we have equal measures. That's all measure means. It's kind of like a proportion. However, in general, this is not what happens. When an electron or when a subatomic particle, when an elementary particle has a choice about what to do, I say choice, of course it doesn't have conscious choice, when there is a possibility of it going one way rather than another, it typically isn't 50-50. The measure of universes is some other proportion. You know, it could be spread amongst 10, 20, 30, as long as they all add up to 100 in the end. It could be any percentage that you like. And when I say any percentage that you like, of course I mean any percentage as determined by the physical laws that are governing that particular event at that particular time. Let's go back to the book. The rate of growth in the number of distinct histories is quite mind-boggling, even though, thanks to interference, there is now a certain amount of spontaneous rejoining as well. Because of this rejoining, the flow of information in the real multiverse is not divided into strictly autonomous subflows, branching autonomous histories. Although there is still no communication between histories, in the sense of message sending, they are intimately affecting each other, because the effect of interference on a history depends on what other histories are present. Not only is the multiverse no longer perfectly partitioned into histories, individual particles are not perfectly partitioned into instances. For example, consider the following interference phenomenon where x and y now represent different values of the position of a single particle. So we've got here x and y, so the particle could be at either position x or at position y. And then these histories join together so that the particle is now at position x. And then at some later time, it differentiates again, the universe differentiates again, such that the particle could now be in x or y once more. And the blurb underneath that picture says, how instances of a particle lose their identity during interference. Has the instance of the particle at x stayed at x or moved to y? Has the instance of particle y returned to y or moved to x? And David's about to explain why this kind of question doesn't really make any sense, because fungibility completely erases, in a sense, the identity of which instance is which instance. It doesn't make any sense to ask the question. Let's persevere. David writes, because these two groups of instances of the particle initially at different positions have gone through a moment of being fungible, there is no such thing as which of them has ended up at which final position. This sort of interference is going on all the time, even for a single particle in a region of otherwise empty space. So there is, in general, no such thing as the same instance of a particle at different times. Okay, just pause there, my reflection. This is just like with the finance example we had right at the beginning of the chapter. If there's $2 in your bank account and the tax office owns one of them, it makes no sense to say which of them is yours and which of them is the tax office. All we know is that one of them belongs to you and one belongs to the tax office, but they're fungible. Even though there are two, there's diversity within fungibility. There's a difference between them. However, we can't say which of them belongs to who. So our usual way of speaking, our language has sort of reached its limits when we start talking about these things, like the multiverse, right at the edge of our understanding of science. And I'll just emphasize now as well the astonishing fact that you yourself are made up of uncountably infinite numbers of instances of yourself, possibly uncountably infinite number. If it's not uncountably infinitely large, then it's certainly a very large number of instances of yourself occupy the space and time where you are now. That's very strange. You might think, what does it mean for me to be made up of many, many instances of myself? Well, it doesn't mean anything over and above what you thought of your self-identity prior to knowing this. When something happens where you actually physically differentiate into two versions of yourself, where you could have gone left or right, and you ended up going left, and copies of you went to the right, you're no longer one of those copies that went to the right. You're only the instances that went to the left. All those instances that went to the right, they're no longer you in a sense. They're copies of you, I would say. All the copies that went to the left, well, they're you. And so you feel the way you feel having gone to the left, and you will never know what it was like to have gone to the right or what happened to that person. It's like the Sliding Doors movie. So what I would say about personal identity is that there are now two versions of you, but you are you, and you are different to the copy that just went to the right. You are only the copies that went to the left. And that continues to happen. There continues to be this branching, if you like. This branching of not only elementary particles, but everything in the physical universe does this as well. Again, amazing, astonishing, but not unbelievable. Not unbelievable. Okay, let's go back to the book. Even within the same history, particles in general do not retain their identities over time. For example, during a collision between two atoms, histories of the event split into something like this. So either we can have the two atoms that apparently collide such that one retains its identity, another retains its identity, having bounced off one another. That's what that first diagram is showing. Or something like that, which is where the two particles pass through each other. In either case, they retain their identities. And David writes, so for each particle individually, the event is rather like a collision with a semi-silvered mirror. Each atom plays the role of the mirror for the other atom, but the multiversal view of both particles looks like this, where at the end of the collision, some of the instances of each atom have become fungible with what was originally a different atom. Pause there, just my reflection. What I was saying before about a human being, okay, this happens for everything, okay, it doesn't just happen for human beings, it happens for any living thing, cats and dogs, it happens for planets, it happens for anything that you like, where something could have happened one way, but in fact happens a different way. Although that differentiation can happen, so far as I know, it's not possible for anything much larger than elementary particles, perhaps atoms, okay, fine, but nothing like a human being can then interfere with itself. It's not like the two instances of you, one set of instances having gone left and one set of instances having turned right, will then recombine and interfere. I don't think that's physically possible. Back to the book. For the same reason, there is no such thing as the speed of one instance of a particle at a given location. Speed is defined as distance divided by time taken, but that is not meaningful in situations where there is no such thing as a particular instance of the particle over time. Instead, a collection of fungible instances of a particle in general have several speeds, meaning that in general they will do different things an instant later. This is another instance of diversity within fungibility. Not only can a fungible collection with the same position have different speeds, a fungible group with the same speed can have different positions. Furthermore, it follows from the laws of quantum physics that for any fungible collection of instances of a physical object, some of their attributes must be diverse. This is known as the Heisenberg uncertainty principle, after the physicist Werner Heisenberg, who deduced the earliest version from quantum theory. Pause there, my reflection, emphasizing the word deduced there. So this is not an axiom or a postulate of quantum theory. It is derived from quantum theory, from more basic things. It is a consequence of the rest of quantum theory. That is what the uncertainty principle is about. So poorly named, as David will explain shortly, but it just means that for any instance, or for any elementary particle, let's stick with elementary particle, like an electron, it doesn't have a super sharp position. It's not in a particular place at any given time. It is spread out in space like an ink blot. So too is its speed. And so, in fact, the way that Heisenberg's uncertainty principle works is that the sharper that you try to make the position of your electron, then the less sharp things like the speed of the electron become. Now, for anyone who's studied classical physics, you don't even need quantum physics for that, you will understand something called diffraction, perhaps, okay, diffraction of light. This is where you narrow a slit through which light can pass, and the more and more narrow you make the slit, the more that the light going through the slit spreads out. It diffracts more and more. This is certainly related to quantum theory, but to a first approximation, we can simply talk about the fact that we are isolating the photons that pass through the slit to a particular point in space. We've narrowed the x value, and by narrowing that x value, the delta x value, the possible positions where it can be, what we make uncertain is all the different ways in which it can have momentum, it can have speed, and so it could go more to the left and more to the right. So the uncertainty principle actually kind of predates quantum theory in a certain sense. There's a version in classical theory just to do with diffraction, simple classical diffraction. Back to the book. David writes, hence, for instance, an individual electron always has a range of different locations and a range of different speeds and different directions of motion. As a result, its typical behavior is to spread out gradually in space. Its quantum mechanical law of motion resembles the law governing the spread of an ink blot. So if it is initially located in a very small region, it spreads out rapidly, and the larger it gets, the more slowly it spreads. The entanglement information that it carries ensures that no two instances of it can ever contribute to the same history. Or more precisely, at times and places where there are histories, it exists in instances which can never collide. If a particle's range of speeds is centered not on zero, but on some other value, then the whole of the ink blot moves, with its centre obeying approximately the laws of motion in classical physics. In quantum physics, this is how motion in general works. Skipping a short bit, and then David writes, now put a proton into the middle of that gradually spreading cloud of instances of a single electron. The proton has a positive charge, which attracts the negatively charged electron. As a result, the cloud stops spreading when its size is such that its tendency to spread outwards, due to its uncertainty principle diversity, is exactly balanced by its attraction to the proton. The resulting structure is called an atom of hydrogen. Historically, this explanation of what atoms are was one of the first triumphs of quantum theory, for atoms could not exist at all according to classical physics. Okay, pause there, just my reflection. The reason why classically atoms shouldn't exist is because in classical physics we knew that, for example, accelerating electrons in a magnetic field causes electromagnetic radiation to be produced. And so this is how radio works, for example, right? So a radio transmitter, well, literally a radio transmitter is like just a piece of metal, right? It's an aerial, it's a wire, and what you do is you accelerate an electron up and down that aerial, up and down the wire, or antenna, I think sometimes it's called. Anyway, the transmitter is a piece of wire. And the faster that the electron goes up and down there, then the higher the frequency of the radiation that escapes from there. But you have to keep on providing energy in order for the electron to go up and down so that you can produce more and more photons of light coming out, okay? Radio photons if you want to create radio waves, okay? And so this is the principle of how radios operate. Electrons vibrate up and down a piece of metal of some sort, okay? It doesn't have to be metal these days. In the mobile phone, it's not necessarily metal. I think it's a carbon aerial or something. Whatever the case, energy is provided to the electrons, making them go up and down, and that creates electromagnetic radiation. Now, if you don't keep on adding energy to this system, to the transmitter, then of course the radiation will stop, the electrons will stop moving. What has this got to do with atoms? Well, if an atom is really an electron going around a proton, then it's the same idea as the aerial. The electron should be emitting photons of radiation of some sort, but in general they don't, okay, except under very special circumstances. The electron is going around but not emitting any radiation, but it should be emitting radiation. And especially because the electron is moving in a circle, so it's changing its direction, well, moving in a circle, moving in a sphere, something like that. It's going around anyway. In order for it to go around in a curved path, that means it's changing its direction. If it's changing its direction, there must be some energy causing it to change its direction, okay? A force has to be applied. And if there is no external source of energy doing this, causing it to change its direction, then there must be an internal source of energy causing it to do that, which should cause it to decay into the orbit to decay into the nucleus. So all atoms should have collapsed on the classical theory, but they don't. So let's just read what David has to say about this. He writes, it used to be a mystery why electrons do not fall onto the nucleus in a flash of radiation. Neither the nucleus nor the electrons individually have more than 1/10,000th the diameter of the atom. So what keeps them so far apart? And what makes atoms stable at that size? In non-technical accounts, the structure of atoms is sometimes explained by analogy with the solar system. One imagines electrons in orbit around the nucleus like planets around the sun. But that does not match the reality. For one thing, gravitationally bound objects do slowly spiral in, emitting gravitational radiation. The process has been observed for binary neutron stars. And the corresponding electromagnetic process in an atom would be over in a fraction of a second. For another, the existence of solid matter, which consists of atoms packed closely together, is evidence that atoms cannot easily penetrate each other, yet solar systems certainly could. Furthermore, it turns out that in the hydrogen atom, the electron in its lowest energy state is not orbiting at all, but as I said, just sitting there, like an ink blot. Its uncertainty principle tendency to spread out, exactly balanced by the electrostatic force. In this way, the phenomena of interference and diversity within fungibility are integral to the structure and stability of all static objects, including all solid bodies, just as they are integral to all motion. So pause there. My reflection here, just to drive that point home. If the classical version of the atom was true, and we had this electron orbiting the nucleus, then indeed the atom would be almost entirely empty space. And if the atom was entirely empty space, then atoms should go through each other. And no matter would really be solid, because you'd have this single little electron orbiting this tiny little nucleus, and when you sit on a chair, you should just go through the chair, and worse than that, you and the chair should go straight through to the core of the Earth, etc. Okay, there should be no solid matter to begin with, if the classical version of the atom was true. But the classical version of the atom is not true. In fact, what's going on is the atom is a multiversal object. And so there are many, many instances of the electron. And because there are many instances of the electron spread around the nucleus like an ink blot, then you can't have one atom penetrating another atom very easily. That's extremely difficult. It happens in certain circumstances when you get into neutron stars and weird areas of astrophysics and whatever. Putting that aside, that's situations where the gravitational force actually overcomes the electrostatic force. But this tendency to spread out means that the negative cloud of any given atom, such as the chair on which you sit, the atoms on the chair on which you sit, and the reason that you can't push one hand through the other hand no matter how hard you push, is because the atoms in one hand contain electrons which are spread out around the atom, kind of like a cloud, but better to say like many of the fungible instances are spread out all around the nucleus, and so too the atoms in this hand. And so the fungible instances here are repelling the fungible instances there, and you can't get matter to go through matter for that reason. Back to the book. The term uncertainty principle is misleading. Let me stress that it has nothing to do with uncertainty or any other distressing psychological sensations that the pioneers of quantum physics might have felt. When an electron has more than one speed or more than one position, that has nothing to do with anyone being uncertain what the speed is, any more than anyone is uncertain which dollar in their bank account belongs to the tax authority. The diversity of attributes in both cases is a physical fact, independent of what anyone knows or feels. Nor, by the way, is the uncertainty principle a principle, for that suggests an independent postulate that could logically be dropped or replaced to obtain a different theory. In fact, one could no more drop it from quantum theory than one could omit eclipses from astronomy. There is no principle of eclipses. Their existence can be deduced from theories of much greater generality, such as those of the solar system's geometry and dynamics. Similarly, the uncertainty principle is deduced from the principles of quantum theory. Thanks to the strong internal interference that it is continuously undergoing, a typical electron is an irreducibly multiversal object, and not a collection of parallel universal parallel histories objects. That is to say, it has multiple positions and multiple speeds without being divisible into autonomous subentities, each of which has one speed and one position. Even different electrons do not have completely separate identities. So the reality is an electron field throughout the whole of space, and disturbances spread through this field as waves, at the speed of light or below. This is what gave rise to the often quoted misconception among the pioneers of quantum theory that electrons, and likewise other particles, are particles and waves at the same time. There is a field, or waves, in the multiverse for every individual particle that we observe in a particular universe. Pause there, my reflection. This can be very difficult to understand. So there is a strict sense in which wave-particle duality is absolutely false. Namely, that within any given universe, like the one you occupy, the electron is like this inkblot thing. I prefer to regard it as more closely related to our concept of particle than anything else. What it's not is a wave. The electron can't both be isolated at a single point and spread out throughout all of space at the same time. The wave function of an electron would suggest that it is spread out greatly throughout a vast region of space. That's what the wave function says, and that's what the wave model of the electron would also suggest as well, if we were going to go down that path and regard electrons as waves. The electron acts far more like a particle, okay, and the experiments that can be done, like the photoelectric effect, show that the electron is in fact far more particle-like. Now that's one thing. The other thing is that the multiverse exists, And that if you could have a God's eye view of the multiverse, then you would see that the electron, for example, to pick one particle, occupies all the physically possible places that the electron could occupy given its wave function. And that would look like a wave across the entire multiverse, across all the universes. Any person in a particular universe can't have access to all those other universes, can't observe those other universes. But someone who was, in theory, like a god outside of the multiverse and looking down at subatomic particles would see that they're in all these different positions. And that multiversal object, which is the subatomic particle, or the electron, would resemble a wave. All of its positions would seem to be a wave, because it would be this continuously changing, varying thing, sometimes commonly in this place, less commonly in that place. It'd have peaks and troughs, and so it would look like a wave. The way in which you would see all the different positions of the electron would resemble something like a wave. Okay, now I'm skipping another paragraph here, and then David writes, "A history is part of the multiverse in the same sense that a geological stratum is part of the Earth's crust. One history is distinguished from the others by the values of physical variables, just as stratum is distinguished from others by its chemical composition, and by the types of fossils found in it, and so on. A stratum and a history are both channels of information flow. They preserve information because, although their contents change over time, they are approximately autonomous. That is to say, the changes in a particular stratum or history depend almost entirely on conditions inside it and not elsewhere. It is because of that autonomy that a fossil found today can be used as evidence of what was present when that stratum was formed. Similarly, it is why, within a history, using classical physics, one can successfully predict some aspects of the future of that history from its past. A stratum, like a history, has no separate existence over and above the objects in it. It consists of them. Nor does a stratum have well-defined edges. Also, there are regions of the Earth, for instance near volcanoes, where strata have merged. Although I think there are no geological processes that split and re-merge strata in the way that histories split and re-merge. There are regions of Earth, such as the core, where there have never been strata. And there are regions, such as the atmosphere, where strata do form, but their content interact and mix on much shorter timescales than in the crust. Similarly, there are regions of the multiverse that contain short-lived histories, and others that do not even approximately contain histories. However, there is one big difference between the ways in which strata and histories emerge from their respective underlying phenomena. Although not every atom in the Earth's crust can be unambiguously assigned to a particular stratum, most of the atoms that form a stratum can. In contrast, every atom in an everyday object is a multiversal object, not partitioned into nearly autonomous instances and nearly autonomous histories, yet everyday objects such as starships and betrothed couples, which are made of such particles, are partitioned very accurately into nearly autonomous histories with exactly one instance, one position, one speed of each object in each history. That is because of the suppression of interference by entanglement. As I explained, interference almost always happens either very soon after splitting or not at all. That is why the larger and more complex an object or process is, the less its gross behaviour is affected by interference. At that coarse-grained level of emergence, events in the multiverse consist of autonomous histories, with each coarse-grained history consisting of a swath of many histories differing only in microscopic details but affecting each other through interference. Spheres of differentiation tend to grow at nearly the speed of light, so on the scale of everyday life and above, those coarse-grained histories can justly be called universes, in the ordinary sense of the word. Each of them somewhat resembles the objects of classical physics, and they can usefully be called parallel because they are nearly autonomous. To the inhabitants, each looks very like a single universe would. Pause there, my reflection. Just recall when I was speaking earlier about how it's rather strange to think that you yourself are made of many, many fungible instances of yourself right now. And when a choice is made in the universe, such as you could have gone left or right, instances of you that have gone right cease to be you, where if you choose to go left, instances of you that choose to go left are still you, until such time as there's another choice to make. However, we don't get interference of human beings. They don't come back together for the reasons that David just says here. Okay, the larger and larger the object becomes, the less and less it's going to be affected by interference. Okay, back to the book. Microscopic events which are accidentally amplified to that coarse-grained level, like the voltage surge in our story, are rare in any one coarse-grained history, but common in the multiverse as a whole. For example, consider a single cosmic ray particle travelling in the direction of Earth from deep space. That particle must be travelling in a range of slightly different directions because the uncertainty principle implies that in the multiverse it must spread sideways like an ink blot as it travels. By the time it arrives, this ink blot may well be wider than the width of the whole Earth. So most of it misses and the rest strikes everywhere on the exposed surface. Remember, this is just a single particle, which may consist of fungible instances. The next thing that happens is that they cease to be fungible, splitting through their interaction with atoms at their points of arrival into a finite but huge number of instances, each of which is the origin of a separate history. In each such history, there is an autonomous instance of the cosmic ray particle which will dissipate its energy in creating a cosmic ray shower of electrically charged particles. Thus, in different histories, such a shower will occur at different locations. In some, that shower will provide a conducting path down which a lightning bolt will travel. Every atom on the surface of the Earth will be struck by such lightning in some history. In other histories, one of those cosmic ray particles will strike a human cell, damaging some already damaged DNA in such a way as to make the cell cancerous. Some non-negligible proportion of all cancers are caused in this way. As a result, there exist histories in which any given person alive in our history at any time is killed soon afterwards by cancer. There exist other histories in which the course of a battle or war is changed by such an event, or by a lightning bolt, at exactly the right place and time, or by any countless other unlikely, random events. This makes it highly plausible that there exist histories in which events have played out more or less as alternative history stories such as Fatherland and Roma Eterna, in which events in your own life played out very differently, for better or worse. A great deal of fiction is therefore close to a fact somewhere in the multiverse, but not all fiction. For instance, there are no histories in which my stories of the transporter malfunction are true because they require different laws of physics. Nor are there histories in which the fundamental constants of nature, such as the speed of light or the charge on an electron, are different. There is, however, a sense in which different laws of physics appear to be true for a period of time in some histories, because of a sequence of unlikely accidents. There may also be universes in which there are different laws of physics, as required in anthropic explanations of fine-tuning, but as yet there is no viable theory of such a multiverse. Pause there, it's my reflection. This is certainly related to what I said in the last episode, if you recall, about these things called Harry Potter universes, places where magic has appeared to have worked, but not places where magic actually does work. Okay, go back to the last episode for that one. And David also mentions there these other kinds of multiverses where different physical laws might actually be true, but they're not scientific theories for now. They are rather metaphysical theories, which is fine. They're all very interesting. And again, in the last episode and the one before that, I think I mentioned these other kinds of multiverse, non-quantum multiverses, much larger sets, or classes indeed, of multiverses. Okay, back to the book. And David writes, some of my own research in physics has been concerned with the theory of quantum computers. These are computers in which the information carrying variables have been protected by a variety of means from becoming entangled with their surroundings. This allows a new mode of computation in which the flow of information is not confined to a single history. In one type of quantum computation, enormous numbers of different computation, taking place simultaneously, can affect each other and hence contribute to the output of a computation. This is known as quantum parallelism. In a typical quantum computation, individual bits of information are represented in physical objects known as qubits, quantum bits, in which there is a large variety of physical implementations, but always with two essential features. First, each qubit has a variable that can take one of two discrete values, and second, special measures are taken to protect the qubits from entanglement, such as cooling them to temperatures close to absolute zero. A typical algorithm using quantum parallelism begins by causing the information carrying variables in some of the qubits to acquire both their values simultaneously. Consequently, regarding those qubits as a register representing, say, a number, the number of separate instances of the register as a whole is exponentially large, 2 to the power of the number of qubits. Then, for a period, classical computations are performed, during which waves of differentiation spread to some of the other qubits, but no further, because of the special measures to prevent this. Hence, information is processed separately in each of the vast numbers of autonomous histories. Finally, an interference process involving all the affected qubits combines the information in those histories into a single history. Because of the intervening computation, which has processed the information, the final state is not the same as the initial one, as in the simple interference experiment I discussed, but is some function of it, like this. Okay, and there's a picture or a representation of what's going on, where in a typical quantum computation, you've got X splitting into all these different possible histories, okay, all these different possible versions. Then interference happens and they all combine together to give you the output function. And David writes, just as the Starship crew members could achieve the effect of large amounts of computation by sharing information with their doppelgangers, computing the same function on different inputs, so an algorithm that makes use of quantum parallelism does the same. But while the fictional effect is limited only by Starship regulations that we may invent to suit the plot, quantum computers are limited by the laws of physics that govern quantum interference. Only certain types of parallel computation can be performed with the help of the multiverse in this way. They are the ones for which the mathematics of quantum interference happens to be just right for combining into a single history the information that is needed for the final result. In such computations, a quantum computer with only a few hundred qubits could perform far more computations in parallel than there are atoms in the visible universe. At the time of writing, quantum computers with about 10 qubits have been constructed. Scaling the technology to larger numbers is a tremendous challenge for quantum technology, but it is gradually being met. Pause there, my reflection. So again, as I've mentioned in previous episodes, once we've got fully functioning quantum computers of the kind David just described there, where the resources classically that would have been required to complete the computation would exceed all of the atoms in the known visible universe, we have to conclude that the computational resources that are actually performing that computation successfully exist somewhere, and it's not in the visible universe. Hence, the multiverse must exist. So once we have that proof, if you like, once we have that evidence or that problem, the only known explanation of which is that the universe and reality is much, much greater than we ever thought, then the majority of physicists, one would presume, will be on board with the multiverse, finally. Now, as of today, like David says, we've got quantum computers back then, when the beginning of infinity was written, of 10 qubits. I don't know what it is today. It depends on who you ask, which university you go to. Sometimes in quantum computation now, there is this issue, don't necessarily say problem, there is this issue where the results of what's going on aren't published, kind of like with pharmacology, where there is a tension between commercial confidence and wanting to keep your intellectual property to yourself, so that your competitors don't have access to the information that you do. So that's on the one hand, you don't want to publish all of your results about how good your quantum computation is or how good your particular medicine is. There's a tension between that and the usual process of peer review and getting other scientists to be able to check your results to see that you haven't made errors. So I literally don't know what the best quantum computer is right now. There are places where things are going very well, where they've got only 4, 6 qubits, something like that. But others are claiming they've got, hundreds of qubits and they're doing things. But there's very few published results, and I'm not up on all that, but I'm sure a Google search will reveal more than what I can teach you here now. Okay, now I'm going to skip a significant part here and move on to something about how discrete changes of energy can occur, especially around an atom. Let's say, for example, where an electron absorbs a photon. When an electron absorbs a photon, remember there are a few things that could happen. One thing that could happen is that nothing observable happens beyond the photon striking the electron and then the photon disappearing and no apparent change in the electron occurring. Or the photon strikes the electron orbiting the atom and the electron moves up an energy level around the atom, so moves up to a higher orbital. Or indeed, if the electron is struck by a photon with sufficient energy, it can knock the electron completely out of the atom altogether. But what we're interested in here is this idea of the quantum, where the electron absorbs just the right amount of energy, such that it moves from one particular energy level up to another particular energy level. And so the photon coming in is a single quantum of energy. Okay. Let's read what David has to write about this particular phenomenon. And he writes, now let us look at the arrival of that single quantum of energy to see how that discrete change can possibly happen without any discontinuity. Consider the simplest possible case. An atom absorbs a photon, including all its energy. This energy transfer does not take place instantaneously. Forget anything that you may have read about quantum jumps. They're a myth. Pause there, just my reflection. You can look at David's Edge question answer on what scientific idea needs to be retired, and he said the idea of quantum jumps. And just Google that, quantum jumps, David Deutsch, and you will find some really interesting material there. Let's keep going. David writes, there are many ways in which it can happen, but the simplest is this. At the beginning of the process, the atom is in, say, its ground state, in which its electrons have the least possible energy allowed by quantum theory. That means that all its instances within the relevant coarse-grained history have that energy. Assume that they are also fungible. At the end of the process, all those instances are still fungible, but now they are in the excited state, which has one additional quantum of energy. What is that atom like halfway through the process? Its instances are still fungible, but now half of them are in the ground state and half in the excited state. It is as if a continuously variable amount of money changed ownership gradually from one discrete owner to another. This mechanism is ubiquitous in quantum physics and is the general means by which transitions between discrete states happen in a continuous way. In classical physics, a tiny effect always means a tiny change in some measurable quantities. In quantum physics, physical variables are typically discrete and so cannot undergo tiny changes. Instead, a tiny effect means a tiny change in the proportions that have the various discrete attributes. This also raises the issue of whether time itself is a continuous variable. In this discussion, I am assuming that it is. However, the quantum mechanics of time is not yet fully understood and will not be until we have a quantum theory of gravity, the unification of quantum theory with the general theory of relativity. So it may turn out that things are not as simple as that. One thing we can be fairly sure of, though, is that in that theory, different times are a special case of different universes. In other words, time is an entanglement phenomenon which places all equal clock readings of correctly prepared clocks, or of any objects usable as clocks, into the same history. This was first understood by physicists Don Page and William Wouters in 1983. Pause there, my reflection. So that's some very interesting stuff there about the physics of time. And David has spoken elsewhere about the physics of time, because the time has this very what was it? Time? I think it was Thomas Aquinas who said something to the effect of, I know exactly what time is until someone asks me. Time has been mysterious for a long time in physics, but there is an interview that David Deutsch gave, and I'll link to it in the description to this video, that I think articulates quite well what time kind of is and why it isn't as mysterious sometimes as many people think. But let's not get distracted by that just for now. And I'm skipping a bit, and I'm skipping to a large part about what I would still call Harry Potter universes, where David is talking about boiling some water, for example. And yes, and this is what in the last episode Brett Weinstein was very concerned about, that sometimes these highly unlikely events indeed happen. And for example, if you're boiling water, David writes, in some tiny sliver of the multiverse, the kettle transforms itself into a top hat and the water into a rabbit, which then hops away, and you get neither tea nor coffee, but rather are very surprised. That is a history after that transformation, but there is no way of correctly explaining what was happening during it or predicting the probabilities without referring to other parts of the multiverse, enormously larger parts with larger measures in which there was no rabbit. Yes, and so there's no reason to reject the multiverse just because there's this tiny, tiny sliver of universes in which some bizarre things happen. And what David writes about this, okay, so where we have a situation where you're boiling water to make tea. Throughout your entire life, of course, every time you boil water to make tea, one would expect nothing particularly unusual happens. But David does say that, well, it's consistent with the laws of physics. It's quite possible for the kettle to turn itself into a top hat and the water to turn itself into a rabbit, which then hops away. So we've got these kind of two versions. The one in which you boil water, nothing unusual happens and you make tea, and one in which you end up with the rabbit. On that, David says, and so I'm skipping a huge amount here from this chapter, from the beginning of Infinity, but I'll just concentrate on the section where he says, quote, "The rabbit history is fundamentally different from the tea history, in that the latter, the tea history, remains very accurately autonomous throughout the period. In the rabbit history, I end up with memories that are identical to what they would be in a history in which water became a rabbit, but those are misleading memories. There was no such history. The history containing those memories began only after the rabbit had formed. For that matter, there are also places in the multiverse, of far larger measure than that one, in which only my brain was affected, producing exactly those memories. In effect, I had an hallucination caused by random motion of the atoms in my brain." Pause there, my reflection. So just to emphasize this bit. Yes, it's possible that indeed a kettle can form itself into a top hat and water can form itself into a rabbit, such that boiling water for tea, leads to this rabbit jumping out of a top hat. But as David says there, not only is that exceedingly unlikely, the tiny, tiny measure of universe in which that happens, but if you actually did have that memory, if that seemed to have occurred to you, the better explanation, according to quantum theory, is that that occurred only in your brain. That there was misfirings of neurons in your brain that caused you to hallucinate that exact thing, rather than that exact thing actually happening. Okay? So quantum theory makes sense out of those things. And David writes straight after that, "Some philosophers make a big issue of that sort of thing, claiming that it casts doubt on the scientific status of quantum theory. But of course, they are empiricists. In reality, misleading observations, misleading memories, and false interpretations are common, even in the mainstreams of history. We have to work hard to avoid fooling ourselves with them. So it is not quite true that, for instance, there are histories in which magic appears to work. There are only histories in which magic appears to have worked, but will never work again. There are histories in which I appear to have walked through a wall because all the atoms of my body happen to resume their original courses after being deflected by atoms in the wall. But those histories began at the wall. The true explanation of what happened involves many other instances of me and it, or we can roughly explain it in terms of random events of very low probability. It is a bit like winning a lottery. The winner cannot properly explain what has just happened without invoking the existence of many losers. In the multiverse, the losers are the other instances of oneself." Skipping a little bit more and reaching the end of this chapter here. And it ends in a very poetic and eloquent way. This won't be the end of the episode, but there'll be the end of me reading the book. So I'm going to read the final 2 paragraphs of the chapter here. And David writes, "We, namely people, we are channels of information flow. So are histories. And so are all relatively autonomous objects within histories. But we, sentient beings, are extremely unusual channels, along which sometimes knowledge grows. This can have dramatic effects, not only within a history, where it can, for instance, have effects that do not diminish with distance, but also across the multiverse. Since the growth of knowledge is a process of error correction, and since there are many more ways of being wrong than right, knowledge-creating entities rapidly become more alike in different histories than other entities. As far as is known, knowledge-creating processes are unique in both these respects. All other effects diminish with distance in space and become increasingly different across the multiverse in the long run. But that is only as far as is known. Here is an opportunity for some wild speculations that could inform a science fiction story. What if there is something other than information flow that can cause coherent emergent phenomena in the multiverse? What if knowledge, or something other than knowledge, could emerge from that and begin to have purposes of its own and to conform the multiverse to those purposes, as we do? Could we communicate with it? Presumably not in the usual sense of the term, because that would be information flow, but perhaps the story could propose some novel analogue of communication which, like quantum interference, did not involve sending messages. Would we be trapped in a war of mutual extermination with such an entity? Or is it possible we could nevertheless have something in common with it? Let us shun parochial resolutions of the issue, such as a discovery that what bridges the barrier is love or trust. But let us remember that, just as we are at the top rank of significance in the great scheme of things, anything else that could create explanations would be too. And there is always room at the top. Okay, and that's the end of the chapter. And there is always room at the top is a reflection of Richard Feynman's quip that there is always room at the bottom. In other words, there is a lot of space down there when you get smaller and smaller than molecules. So you can store a lot of information in small stuff. And David there is reflecting that there is always more and more space out there as we get larger as well. Now, David has ended the chapter there with mention of interesting science fiction stories. And so it's also the way he began the chapter, with an interesting science fiction story. And I have been promising for about 4 episodes that I would explain the way in which the multiverse can be tested against other interpretations of quantum theory, like any collapse model, for example. Now, I'm not going to talk about ways in which we can test the multiverse theory against, for example, things like the Bohmian pilot wave model, as David has explained even recently. These are versions of quantum theory which really are the multiverse in heavy disguise. I might mention the Bohmian theory shortly, but what I want to do now is to tell a story, to tell a science fiction story about how to test an experimental test of the multiverse theory against the Copenhagen interpretation, against any other interpretation that involves the collapse of the wave function. And so for that, I'm going to have to change venue. So here we are for the long-promised explanation of how the multiverse is testable. Now, in previous episodes, I have actually explained certain ways in which the multiverse is experimentally testable. But today, I'm finally going to get to David Deutsch's own experimental test of the multiverse interpretation versus all those other kinds of interpretations of quantum theory, namely the ones that involve so-called collapse of the wave function, so collapse models. Now, the way in which I'm going to explain this experiment is not by simply reading David's papers that he's written on this, or even going to some other popular accounts of it, but rather I'm going to try and turn it into a story. And the reason for doing it this way, the reason for telling a story, the story of the experiment, is the experiment isn't practically feasible right now, but it will be one day. So it's kind of like how the Higgs boson, this particle that gives other particles mass, was postulated long before there was an actual practical way of testing. It took the Large Hadron Collider, a piece of scientific apparatus much larger than anything else that had gone before. It took decades before the hypothesis of the Higgs boson could be tested by experiment, or rather, before the theory of the Higgs boson could be tested by experiment, namely the Large Hadron Collider, smashing particles together and seeing what came out and seeing if we could actually observe the Higgs boson. Of course, as Popperians, what we say is that we weren't confirming the existence of the Higgs boson, we were refuting all the other ideas about what those observations could mean, namely if the Higgs boson was some other kind of particle. So every other theory about what was going on in those experiments was refuted, but the Higgs boson explanation of the observations was not refuted. And so therefore we say that those experiments from the Large Hadron Collider did indeed reveal the existence of the Higgs boson. All right, so now it's story time. This is a science fiction story. So perhaps sit back, get yourself a nice cup of tea, and enjoy being transported to the future. So picture it. It's the year 2075, and though quantum computers are now carried in the pockets of most people, David Deutsch's proposed test of Everettian quantum theory against other so-called collapse models has yet to be performed. Many artificial general intelligences actually now populate the Earth, and while many silicons, as the new general intelligences are happy to be called, choose to house their minds within bodies that closely resemble those of typical humans, others choose to take the form of cars or aircraft. Some few even choose bodies that double as spacefaring vehicles, because without the need for oxygen, or indeed air of any kind, they can routinely explore the darker reaches of the solar system, just for fun. Some of these intelligent spacecraft are very large indeed, as they may carry huge payloads of batteries, and some also choose to be employed as cargo vessels, shipping resources between Earth and other bodies in the solar system. Now, one of these space silicons, and the hero of our story, is called Parlox Cubite. Parlox has what in the year 2020 would be regarded as a very unusual body for a person. He has the shape of a very long, about 100 metres, and very wide, let's say about 50 metres, box, which is not very deep. It's only about 5 metres deep. So this is his body. His body is a box. This is useful for carrying cargo. Only a small portion of his body houses batteries and a landing gear and rocket fuel for landing and takeoff. Parlox can land in any number of configurations and generally takes off in such a way as to minimise his cross-sectional area and reduce air resistance on low-gravity moons. He's an explorer, this Parlox. He likes to move between places in the solar system that no one else has been to before, and so this is why he's chosen the body that he has. Now, on a particular day, somewhere in 2075, Parlox is travelling from Earth to Jupiter's moon Europa. It has long been known that the radiation saturating the surface of Europa from Jupiter is too intense for any regular human to endure. So despite many probes over the years visiting the moon, few people and no manned missions have ever landed there. Parlox is a physical chemist by training and wants to investigate the ocean beneath the ice on the surface for signs of life. So far, no other missions have found any evidence at all. The journey to Europa is 2 months long, and though he could enter a kind of hibernation state, most silicons have found, for reasons yet to be known, that the hibernation state tends to cause uncomfortable nightmares about 3 days in, and terrible dizziness upon waking. For this reason, on long journeys like this, Parlox chooses the best known sleep-awake cycle. Sleep 7 hours, wake 7 hours, sleep 9 hours, wake 9 hours, repeat. He also has a list of tasks he's set himself to keep himself occupied. One item on the list that he's particularly excited about refers to a message in his ongoing correspondence with the now 122-year-old Professor David Deutsch. Parlox asks whether he might be able to conduct an adapted version of Deutsch's test set out in Section 8 of his 1985 paper, Quantum Theory as a Universal Physical Theory, as published in the International Journal of Theoretical Physics, Volume 24. David and Parlox plan to co-author the paper in which the results will be published and finally perhaps putting to rest what they regard as almost 150 years worth of nonsense in the foundations of quantum theory. Parlox's huge body is, right now, empty, and an almost perfect vacuum isolated from any other matter as it travels through the emptiness of space. But inside his cavernous body is one of the most perfect Mach-Zehnder interferometers ever to have been created. The half-silvered mirrors, near perfect. The laser, perfectly able to attenuate the beam down to just 1 photon each microsecond, second, or even hour if you like. The detectors, the most sensitive ever created. There are 2 regular mirrors in the experiment, regular except for one thing. These mirrors are directly wired to Parlox's mind. So I'll just say that again. These mirrors,
that are inside Parlox's body are directly wired to his mind. Much like the retinas in our eye are directly wired via the optic nerve to our brains and our minds. So Parlox has a very special sense organ. Parlox can detect the slightest vibration of these mirrors due to a collision with something as small as a single photon. Parlox has a mind running on a brain with switching speeds as fast as the speed of light, as all AGI in the year 2075 do. And so he is able to record and transmit data at this speed. Now, I've got a schematic here, a picture of the internal workings of Parlox's sense organ that is the mirror setup. And as we can see, the inner workings of this particular organ, if you like, in Parlox's brain are very similar to the Mach-Zehnder interferometer. So we've got some source of photons, the half-silvered mirror, where the beam will be split into an up part and a down part. That's the U and the D. The regular mirror there is Parlox's sense organ. It connects that regular mirror via some cable, some wire, some nerve off to Parlox's mind. A similar thing with the other regular mirror that is on the down part. And then, as usual in the Mach-Zehnder interferometer, we've got a couple of detectors there, detectors 1 and 2. Now, Parlox has carefully set up the lengths of the U, the up path, and the D, down path. According to collapse theories, like the Copenhagen interpretation, indeed, according to any interpretation that is not literal quantum theory, saying all possibilities really do exist, namely a multiverse, when a photon is emitted at the source, it makes no real sense to ask which of the paths the photon takes. It simply has a 50% chance of going along the U path and a 50% chance of going along the D path. If no one observes which of these paths it goes along, then the photon will be detected with 100% probability at detector 1 and 0% probability at detector 2. This is because of how Parlox has set up the experiment, namely by ensuring that the path length of U and D is slightly different, but the details do not matter. And I've mentioned this in an earlier episode as well about the details of how the Mach-Zehnder interferometer works. What the collapse interpretation says, as do other interpretations, is that some sort of interference effect has happened, and that when the photon is finally detected at detector 1, all the possibilities have collapsed into one. But what the collapse theory also says is that if anyone were to observe the photon mid-flight, for example, if they knew it was travelling along the D path and not the U path, then the interference effect would be destroyed, and we would have 50% of the photons going to detector 1 and 50% to detector 2. In other words, there is a special kind of physics of observation in quantum theory. Observation has a special effect in the world. So this is on the Copenhagen or any so-called collapse theory. Observation has a special role in the world. It has special physics. Anyone who says that the wave function collapses or wonders about what happens during collapse or why it collapses and so on, these people believe in alternatives to the multiverse. But on the other hand, proponents of the Everett way of understanding quantum theory, the realistic way of understanding quantum theory, the literal reading of the equations of quantum theory, is to say that no such collapse happens. Observation has no special role. Observation does not cause the collapse of the wave function. There is nothing special about observations on this view. The so-called measurement problem, as it's sometimes called, is solved. It dissolves away by saying there is no special physics of measurement. So when it comes to the inner workings of Parlox's brain, his sense organs going on here, the Everett understanding of this is that both possibilities happen. Both the up and the down paths are followed, and this in fact explains why interference effects occur. The photon is fired from the source. The photon is in fact a multiversal object. When the photon encounters the half-silvered mirror, all the universes in which the experiment occurs differentiate into two groups. One in which the photon takes the U path, and another group in which the photon takes the D path. This is the only difference between the two groups of universes. These two universes then recombine at the second half-silvered mirror, just prior to the detectors. And it is the literal collision between these two photons, the photons at the U and the D path, that caused the new recombined photon to set off the detector at detector 1, but not detector 2. Now the key thing here for the year 2075, and for Parlox, and what we're now able to do in the distant future, is that Parlox is in fact able to sense the collision of a photon at either of the regular mirrors, because he has a sense organ. So he is able to observe interference going on prior to it happening. So Parlox's sense organs are part of the experiment. His sense organs are those mirrors, those regular mirrors. He can detect if photons are striking those mirrors. And so he is an observer of the experiment while it's going on. Hitherto, impossible to do, because we humans don't have such sense organs. But an artificial general intelligence of the future could have such a sense organ, could build themselves such a sense organ, and perform this experiment. According to the collapse interpretation, this should cause the interference effect to be lost, because it has been observed. According to those interpretations, i.e. all other interpretations besides the multiverse, observation plays a key role in physics. It causes the collapse of the wave function. At least it is supposed to. So in this view, if we repeat the experiment, we should see half the photons to be detected at 1 and half at 2, no matter what, if Parlox is sensing, that is to say, observing them with his sense organs, the regular mirrors. And if indeed the interference fails to occur during this observation experiment, during this interference experiment, and Parlox is observing it, then we have refuted the multiverse theory. This is the sense in which the multiverse is testable. We can refute, we can test, we experimentally test and falsify the multiverse theory. Of course, we have no real alternative, but according to the multiverse account of things, no collapse happens so long as Parlox keeps the information about which mirror he has detected a collision at to himself. Here's what goes on according to literal quantum theory, i.e. according to the multiverse. The photon at the first half-silvered mirror causes the differentiation of the universe into two groups. In half the universes, the photon travels the D path, and Parlox in the D universe detects the collision with the photon. In the other half of the universes, Parlox detects the photons having travelled the U path. Parlox himself actually splits into two separate versions. In either case, Parlox U or Parlox D, in whichever universe, he can record and transmit back to David an intermediate result and say, I can testify that I have observed a photon travelling along one and only one path. It must be the same message in either case. Now the distances D and U are long, and it takes light some time to traverse this path. So Parlox does indeed have time to do all this because he's got a fast brain, remember. But very soon after he sends that message, the message that says, I have detected the photon striking one of my mirrors, and only one of my mirrors, he then sends another message. And he repeats the experiment again and again, as good scientists do, sending message after message back to David, who's part of the experiment. If the messages went something like this, I have detected the photon at one and only one mirror, then the next message comes, I have detected the photon at detector 2, and then I have detected the photon at one and only one mirror, I have detected the photon at detector 1, I have detected the photon at one and only one mirror, I have detected the photon at detector 2, and so on. In other words, roughly half the time detector 1 is activated and half the time detector 2 is, because the photon only ever takes one path, either the U or the D path. It does not take both paths simultaneously. If this was to happen, the multiverse is refuted. However, if the message was to run this way, I have detected the photon at one and only one mirror. Time delay. I have detected the photon at detector 2, and then I have detected the photon at one and only one mirror. Time delay. I have detected the photon at detector 2, etc. It keeps on detecting it at detector 2. Then interference has happened, despite the fact the photon was observed at only ever one of the mirrors. What this means is that the act of observing the photon has not collapsed the wave function. And though the photon was detected at only one mirror, something travelled along the other path, in another universe, shoving aside the photon each time. And this collision forced the recombined photon to travel always into detector 2. Now it's crucially important that Parlox tells no one which mirror he observed the photon strike, because this ruins the experiment. It ruins the experiment because once he says, I detect the photon having struck only one mirror, and that is the mirror corresponding to the U path, this means that the universes have differentiated still further and cannot come together again to interfere. They cannot become fungible once more. The interference can happen if, and only if, the only thing that is different between them is the path of this single photon. If other things start to change, like for example, Parlox sends David a message that the D path was the one travelled, then David also knows in which universe he and Parlox are in, and that is a difference in that universe outside the experiment. This is called decoherence, by the way. Decoherence is where information is leaked out of the experiment into the world, differentiating the universes. Moreover, the message itself will carry different information in the two universes, making them quite different and increasingly different as the energy of the message, as it travels back to the Earth, collides with objects in the solar system. We need to keep the differences only and exclusively inside of Parlox's mind, and effectively this entire apparatus is in Parlox's mind or brain, shielded as it were from the rest of physical reality. This might seem awfully contrived. This might seem bizarre. What on earth are we doing in the year 2075? Why do I have artificial general intelligence? Don't blame the multiverse theory. This bizarre way of testing the multiverse is not the fault of the multiverse theory. It's the fault of the so-called mainstream Copenhagen interpretations or any of the collapse models. They're the weird theory that requires a weird test to refute. That's all. It is those theories that says there is a special role for observers. And so we need to be able to test this special role of observers. It is observers on that account, on that Copenhagen account, on the collapse models account. It is those theories that say there is a special role for observers. That special role is that the observers collapse the wave function. That's what all other interpretations say. That is the spooky and strange claim. So to rule that out, that's why we need this elaborate method inside of a mind to test the claim that observers or minds or something like that is causing the collapse, the vanishing of all the possibilities except for one. If we can rule out this single universe model by having interference between two universes occur within a single mind, then we refute the observer dependence of quantum theory. With the many worlds idea of Everett, and more precisely Deutsch, who replaced the concept that Everett had of branching of a small number of universes into a larger and larger number, and instead David said, well, that's not quite right. It's not that we start off with a small number and that number gets greater and greater and greater over time as quantum phenomena occur, but rather he said that the number of universes that the number of universes that exist all the way back to the beginning of time are constant in number and began fungible, but then differentiate when the possibilities arise. We conclude that the single universe theory and collapse models can be refuted by this means. The only known explanation is that the multiverse did split or differentiate into two different groups, a U group and a D group. And these universes then interfered with each other in such a way that the photon is only ever detected at detector 2 and never at detector 1, despite the fact it was observed by Parlox at only one of the two mirrors. And this was possible because Parlox really did split into two versions of himself, different only to the extent of observing a single photon along the D path or along the U path. Now, what this might be like to split into two copies that are no longer fungible and then to come back together to have these kind of sense organs is anyone's guess at all, but I guess he was having fun. After all, he did know that he was going to be co-authoring a paper with David Deutsch about the fundamentals of physics, so that must have been pretty exciting. Once the experiment is over, it makes no sense to ask Parlox, which mirror did you actually detect the photon at? Was it the mirror on the D path or the mirror along the U path? Parlox won't be able to say, because the two versions of Parlox, and indeed the whole two groups of universes, have recombined at the second half-silvered mirror. Parlox simply cannot remember, because he split into two different copies, one of whom experienced U and one of whom experienced D, but he only recalls ever having experienced one. This is where language kind of breaks down. He both experienced both and one simultaneously. Very strange. So language somewhat fails to capture what is going on here, but the truth is he was both copies for a very brief amount of time. And again, whether this felt like something special or nothing particularly special, we may be able to interrogate him about that. But he'll never be able to tell us which mirror he detected the photon at once he becomes fungible again, once the two versions of him combine together to become a single version of Parlox once more. So he will, in fact, be the first Earthling ever to have experienced this sensation of knowing he was in two universes at the same time and then becoming one version of himself in one universe again. Now, that's if it all works out as predicted by the multiverse. But what if he does not have this experience of being in and conscious of two different non-fungible universes simultaneously? Well, then the whole experiment would refute the multiverse because observation apparently would collapse the wave function. Or better to say, the multiverse itself is simply refuted. The point is, if the experiment works as predicted, there is no way of explaining any of it by recourse to a collapse model where all the universes but one cease to exist. So if indeed the interference fails to happen as predicted, then Parlox's experiment, David Deutsch's experiment, has roundly refuted the multiverse. Quantum theory would then have a hugely open problem about how observation works and why it is so fundamental to the nature of the universe. We would need to develop a new physics of observation and measurement. And physics would become, in part, fundamental physics would become in part about us, about people, and how it is that our choice to observe stuff or not can cause the majority of reality to vanish in an act of performing a scientific experiment. When we choose to perform a particular experiment, we're causing the collapse of the wave function, the collapse of all these other realities that come to bear, causing the result of the experiment to be the way it is. Whereas the multiverse just says all those realities really do continue to exist. Whatever the case, the multiverse is eminently testable by this technique and in principle falsifiable. So that's that. After many months of promise, I hope this satisfies some of you on the most contentious point when it comes to the multiverse. Or perhaps not the most contentious point, one of the most contentious points. Namely that the multiverse is a testable theory from a number of different angles. There are experiments possible, and the strange experiment here, again, is not the fault of the multiverse. It's the fault of the collapse models that propose observation as a fundamental thing that affects reality. So we need an experiment that could possibly refute this idea. And David's version of this is different to the one that I've just told. Mine is based entirely on his. Of course, errors are completely mine, but I thought that because we'd already explained the Mach-Zehnder interferometer, I wanted to explain that way of doing this experiment. Now, the way that David does it is via looking at this thing called the Stern-Gulach experiment. Pronunciation may be wrong there. And a property of subatomic particles called spin. And so rather than attempting to explain all of that, I've stuck with what I hope we're already familiar with if you've been bearing with me through this multiverse series. And on that, this video doesn't quite finish the multiverse series, but for now it does. I have a couple more things to say about the multiverse, but we're going to save those for a more distant episode. For now, I wish to move on to the next chapter, chapter 12, A Physicist's History of Philosophy. And that should be a lot of fun because bizarre as some of the things that we've been talking about during this series have been, like the claim, for example, that your observations can cause vast parts of physical reality to cease to exist. The reason why people, including very smart people, very smart physicists, might come to endorse or insist on such ideas or do very bizarre things like reject the multiverse, is not because of the science, but it's because of their philosophy, bad philosophy. And an overview of bad philosophy by David Deutsch is just the remedy for undoing poor thinking on this point. And it will help us to understand why quantum theory in particular, has a special place in the hearts of many, many philosophers because of this bad philosophy. So the scientific community has sort of treated quantum theory in a way that's somewhat different to the way it treats any other scientific theory. But we'll get on to that. We'll get on to why bad philosophy has come to taint our understanding of quantum theory and hampered progress in quantum theory next time. Until then, bye-bye.